BioniChaos should be live in theory. Okay, should be live. Should be able to hear myself. Maybe. Just checking the right microphone. Yeah, that's working fine. Okay, I only have a few slides for now. As per usual, everything we do is available on BioniChaos.com. Go check out the website. Let us know what you think. And yeah, we had something else that we meant to say that our CEO wants us to say. Shall we follow instructions from the CEO? Yeah, this one, BioniChaos is an open source project creating science simulations and biomedical data tools. We is me and AI tools, build free interactive web apps that uniquely incorporate game mechanics, maybe, and artificial intelligence to make scientific discovery more engaging and intuitive for everyone, blah, blah, blah. Yeah, we had a better one. Yeah, I can't find it. Anyway, you get the drift. Go check this site. Now we very quickly will cover this interactive evolution simulator, so you can control a bunch of parameters. This is not my area of expertise. This one was running already for 62 generations, essentially doing 300 steps per generation. And those creatures that have an eighth genome. Oops. Okay, didn't realize when you change parameters. You restart the simulation entirely. So if you have a genome length of 4 and 1 internal neuron, you can have different go east. You can see how they perform. Well, yeah, they will be taking their time. What's the default value? Yeah, 8. A genome length of 8 and internal neuron number of 2. If you do the go east, they speed up this thing. Yeah, they're essentially smarter. Can I? No, every time you change a parameter, it will actually restart the simulation. How are they able to go around the barrier? The barrier is not doing much. Let's do, the default. Let's do the default. And we are losing viewers, so we'll just go notebook LM to summarize this thing.
Okay, let's unpack this. Imagine a miniature world running entirely on code. And in this world, only the fittest digital beings actually get to pass on their genes. Sounds a bit like some twisted reality show, doesn't it? Well, today we're diving right into exactly that, an interactive evolution simulator. We're jumping straight into this fascinating, maybe slightly morbid playground of natural selection. Our mission today is to really dissect how this remarkably simple model, reveals the core mechanics of evolution and why a strict, unyielding lifespan is absolutely key to its brutal efficiency, and also what chillingly effective behaviors emerge when you give these tiny digital brains just enough information to be, frankly, terrifyingly efficient. So get ready to peek into a world where digital creatures live, die, and evolve with this ruthless, almost disturbing speed.
It really is. It's a stark and elegant illustration of evolution stripped totally bare. This simulator, and it was inspired by David Randall Miller's video, I programmed some creatures. They evolved.
Hmm.
It basically distills the fundamental processes down to their most, well, unforgiving basics. At its heart, you've got these digital creatures, right? Each one has a unique genetic code, a genome, and this genome dictates the wiring of its neural network brain. This brain is their tiny decision-making machine, essentially wired to respond to very basic sensory info and execute actions to navigate their little world.
And when you say brutal basics, I think you really hit the nail on the head there. There is absolutely zero hand-holding in this digital ecosystem, is there? So how does this no-mercy approach actually play out in the simulation? What's the core loop driving this almost cold digital Darwinism?
Right, it revolves around three core stages, absolutely unforgiving stages that just cycle endlessly. First, they live, but here's the catch. Every creature gets a painfully finite existence, precisely 300 steps.
300 steps, wow.
Yeah, and this isn't just some random number they picked. It's a simulated lifespan. People call it the death clock.
Mm-hmm.
And it's crucial, utterly crucial, because it actively selects for ruthless efficiency.
Efficiency.
Exactly. Without this fixed time frame, a creature could, theoretically, just bumble its way to the goal eventually, purely by chance. But by imposing this strict limit, the simulation forces the evolution of brains that can move purposefully, directly, and most importantly, quickly.
Ah, so speed is paramount.
Speed and direction's a digital echo of nature's harsh realities. Find food, find shelter, find a mate, whatever the goal is, do it fast, or you're simply out of the gene pool. It kind of shatters that misconception that evolution is always this slow, gradual march. Here, it's a frantic sprint to efficiency.
Okay, so it's not just reaching the goal, but reaching it fast and, well, smart. That must be where the selection part comes in. Survival of the fittest, quite literally applied.
But hang on, what if a creature just got incredibly lucky in its 300 steps? How does the simulation ensure its actual fitness being selected, not just, random good fortune?
That's a really good question. And it's where the simulation's elegant brutality really shines. At the end of each generation, after those 300 steps are up, a specific fitness criterion is applied. For instance, did the creature reach a designated target area? Simple as that.
Okay.
Only the fittest creatures, the ones that successfully met that goal, are selected. The others, well, they simply die.
Die, like deleted. Exactly. They are completely irrevocably removed from the gene pool. Poof. Gone. There's no second chance, no participation trophy here, absolutely no redos. This clean, no-fuss elimination ensures that only successful strategies, however they were achieved, contribute to the next generation. It drives the population towards increasingly optimized behavior. It's stark, undeniable visual proof that random changes filtered by these brutal constraints can lead to what looks like intelligent design.
Without any designer.
Precisely. No master plan needed at all.
Right. And for the lucky survivors, the ones who made the cut, they get to reproduce. This sounds like where the magic happens. Or maybe the delightful chaos of new mutations comes in. So once these creatures survive, how do they make sure their good genes actually get passed on? What's the reproduction process in this rather cold digital world?
Indeed. The selected survivors, they pass their genomes to the next generation, and they do it through a couple of key mechanisms. The first one is crossover. Their genetic code is basically combined with another survivor's code. It mimics the gene mixing you see in sexual reproduction.
Okay, mixing it up.
Yeah, and critically, there's mutation. This introduces random, often tiny, changes to the genetic code during the copying process.
Ah, the errors. The potentially useful errors.
Exactly. This is the real engine of adaptation, is where new, potentially successful, or sometimes disastrous traits emerge. So over many, many generations, you witness complex, incredibly efficient strategies just popping up, all from these surprisingly simple, cold rules. It's like watching evolution on fast forward, a constant cycle, life, death, modification.
It's kind of ironic, though, isn't it? We're talking about these complex emergent behaviors, but when you look at what these creatures actually know about their world and what they can do, it's almost comically limited. I genuinely wonder how they manage to achieve anything sophisticated at all. Tell us about the digital mind of these little beings.
You're right to wonder. It's a powerful testament to how much complexity can truly arise from minimalism. Quite amazing. Each creature's brain receives only 5 distinct pieces of information from its environment on every single step. Just 5. These are the only things it knows about its world. Their inputs are their X position and Y position. That gives them their precise location on the digital canvas. They also know their age, which is just how many steps have passed in the current generation, ticking up from 0 to that dreaded 300.
The death clock counter.
Exactly. And there's border distance, telling them how close they are to the nearest wall or edge. And finally, something called an oscillator. It's just a rhythmic signal that cycles over time. It potentially allows their brains to develop time-based behaviors, maybe coordinating movements. But that's it, 5 bits of data. It's like trying to navigate a complex maze blindfolded, with only a ticking clock and someone occasionally shouting how close you are to a wall. Every second counts.
Wow, that sounds like a truly tough final exam with only 5 things to go on. So, okay, with those incredibly limited senses, what can they actually do? What are their actions? How do such basic movements combine to create anything like sophisticated navigation?
Well, their actions are equally fundamental. Really basic stuff. Based on those few sensory inputs and the intricate wiring of their evolved neural network, a creature can perform just 4 types of actions, that's all. They can express a desire to move X, that's left or right, and move Y up or down.
Okay, directional.
Yep. They can also have an impulse to move forward, which just continues them in their current direction, and perhaps surprisingly, move random.
Move random. That sounds counterproductive.
You'd think so, but it can be incredibly useful. It might help them get unstuck from a corner or just explore a new path when other options seem blocked or aren't working. A little bit of randomness can sometimes break a deadlock. But what's truly astonishing here, what really gets me, isn't just that evolution works in this system. It's that it doesn't seem to need intelligence or foresight or even complex rules to get going. This simulator basically proves that ruthless elimination of the unfit, combined with random mutation, is really all it takes to build what looks like genius behaviors from scratch. You have these minimal inputs, these minimal outputs, yet through countless generations of this harsh selection process, these creatures develop incredibly complex adapted behaviors, like efficiently navigating mazes or reaching distant goals with surprising directness. It's like watching a master artist create a stunning painting using only, 3 primary colors. It's remarkable.
And it gets even more interesting because we get to step in, right? We can play digital gods in this simulation. We can fiddle with the parameters and essentially influence the entire course of this digital evolution. So how do we, the users, manipulate these rules? How do we push these creatures in different directions?
Yeah, that's where the interactive part really comes alive. Users can adjust several core variables that directly impact the whole evolutionary process. For instance, you've got population. That just controls the raw number of creatures in each generation.
More cannon fodder, potentially.
Well, yes. More creatures typically mean more genetic diversity, more raw material for selection to work with. But there's a trade-off. It also demands significantly more processing power from your computer. Right.
So it's a balance between evolutionary potential and, how long you're willing to wait or how powerful your machine is.
So a bigger population might find a solution faster, maybe, but your computer might really start to groan a bit under the strain.
Oh.
Makes sense. What about mutation? That sounds like it could be a truly chaotic parameter, or maybe incredibly beneficial.
Oh, it is absolutely critical. And it really dictates the pace and the stability of evolution within the simulation. Mutation adjusts the probability that any given gene will randomly change when passed on. A high mutation rate, that introduces rapid variety, constantly shuffling the genetic deck. It can speed up discovering new solutions.
That's true evolution.
Potentially, but it can also destabilize successful genomes. You might get lots of chaotic or less efficient behaviors. Think of it like a toddler getting into a well-organized closet and just throwing things around.
Okay, I get the picture. Right. On the other hand, a low mutation rate leads to slower, more stable evolution. It lets successful traits really solidify in the population. You can literally watch evolution either sprinting erratically or crawling steadily just by tweaking this one slider.
And then there's the brain power aspect you mentioned, genome length and internal neurons. What do those sliders do to the creature's potential cunning? Is it a simple case of bigger brain, better survivor?
Broadly, yes, you could kind of say that. They define the potential complexity of the creature's brain. Longer genomes mean there's space for more neural connections, a greater capacity maybe for storing information about how to act, allowing for more complex behaviors to potentially evolve.
More connections, more complex thoughts.
Something like that. Similarly, more internal neurons provide additional processing nodes within the brain, little connection points. This enables more intricate information processing between the creature's limited sensors and its actions.
Sure.
These settings hint at the potential for, say, multi-step strategies or more nuanced decision-making to emerge over time. And it's not guaranteed, but the potential is there. And of course, there's speed, which just sets how fast they visually move across the screen for our viewing pleasure.
Hanger.
Doesn't affect the evolution itself, just how fast we see it play out. And the real beauty is you can then test these evolving populations against different scenarios. These act as the environmental pressures.
Like different challenges.
Exactly. You have simple ones like Go East, which is just a basic directional challenge. Forces them to find the most direct path eastward. Or the Barrier Challenge, which is more interesting. It forces navigation around obstacles placed in the world.
Ah, maze running.
Sort of. There's also Corner Seeker, where they have to find a specific corner of the screen. These are the digital equivalent of real environmental pressures, forcing very specific adaptations from the evolving creatures. For the Barrier Challenge, for instance, you might see them develop surprisingly elegant curving paths to avoid walls smoothly. Well, in Go East, they'll probably just evolve to blast straight ahead, ignoring everything else, because that's the most efficient way. It's like setting different tasks in a rather brutal reality show.
Speaking of challenges and maybe brutality, this simulation is clearly just a starting point. The creators themselves have proposed some future directions that frankly make it sound even darker, and of course even more interesting from a scientific perspective. Tell us about the kill neuron. That sounds intense, almost dystopian for these little digital guys.
Ah, the kill neuron, yes. This is where it gets really fascinating and, yeah, I agree, a bit unsettling perhaps. Imagine introducing actual predation into the system. Creatures could evolve the ability to hunt and, well, eliminate other creatures within the simulation. Yeah, this would add a profoundly complex and, frankly, cutthroat layer of selection pressure. Suddenly, it's not just about surviving the environment, like reaching a goal or avoiding a wall. Creatures would also need to survive each other.
Predator versus prey, digitally.
Precisely. This would inevitably lead to coevolution. You expect to see digital predators evolving more cunning hunting strategies. And in response, digital prey evolving better evasion tactics, maybe even developing things like digital mimicry, or perhaps alarm signals of communication evolves.
Wow.
It's evolution at its most raw, its most brutal, distilled into code. And it really makes you wonder, doesn't it, how much our own social structures, maybe even subconsciously, are shaped by similar unseen kill neurons in a metaphorical sense, competitive pressures.
I can just picture it. Little digital creatures developing these elaborate cat-and-mouse strategies, or maybe even forming digital herds for protection if sensing others becomes possible. What other dark and interesting ideas are on the horizon for these simulators? Ways to truly push the boundaries of emergent complexity?
Well, beyond the direct conflict of the kill neuron, there's potential for even greater cognitive complexity within the creatures themselves. Imagine allowing for more genes in neurons, significantly larger genomes, many more internal neurons.
Even bigger digital brains.
Right. This would give creatures a much greater capacity for memory, potentially, and more complex decision-making. You might see sophisticated multi-step strategies emerge, rather than just the simple reactive movements we often see now, like remembering where a food source was or planning a route. Then there's the idea of more senses and actions. Think about creatures being able to sense, say, population density around them.
Knowing if it's crowded.
Exactly. Or sensing the proximity to other specific creatures. Maybe even being able to emit digital pheromones to communicate with others.
Digital smells. That could get complicated fast.
It could. Imagine the complex digital social dynamics that might emerge. Or perhaps new actions, like being able to drop temporary barriers or signal to others. And finally, one of the most intriguing ideas is environmental dynamics. The environment itself isn't static anymore.
The world changes.
Yes. Food sources could appear, deplete, and maybe regrow. Safe zones could move location over generations. This forces populations into continuous adaptation. They can't just settle on one optimal strategy because the game keeps changing. This truly reflects the unpredictable, ever-shifting nature of real-world ecosystems much more closely. And all this really raises an important question, I think. How much complexity and what seemingly intelligent behaviors can actually emerge from such simple, often brutal underlying rules? And what does that imply about evolution in general, both in the natural world and potentially in other complex systems we see around us, like economies or social networks? It truly makes you think about the fundamental principles at play.
So, wrapping this up, what does this all mean for you listening in? This deep dive into a simple simulator really shows us, in stark digital terms, the raw, undeniable power of natural selection. It's efficient, it's definitely brutal, and yet it's surprisingly elegant in how it molds these digital creatures to thrive or perish with absolutely no outside designer or plan needed.
Yeah, if we connect this to the bigger picture, it really highlights how these fundamental principles, Things like limited resources, limited time, intense survival pressure drive incredible adaptation across all forms of life, digital or biological. It also makes you wonder, doesn't it? If these simple digital creatures can evolve such cunning, complex strategies from just a few lines of code and some basic rules, what does that suggest about the unseen rules or pressures influencing our own adaptations, our own decisions? Or the seemingly designed complexity we observe everywhere in nature? Maybe think about your own 300 steps in life, the finite resources, the deadlines, the challenges you face. What efficiencies are you being forced to evolve to reach your goals? And perhaps, just perhaps, what small mutations in your own approach might you need along the way to adapt and succeed?
Not sure what's going on here with the survival rates seem to be extraordinarily high, and yeah, potentially there is a bug in the code or something, because even with very low, whatever the lowest on the scale of genome length and the number of internal neurons, the survival rate is still pretty high. So I'm not sure what's that all about. So we have a population of 500. Mutation rate is 0.5. So I don't know how that affects anything. Let's just keep it at the default value for now. And start the simulation. Okay, it's jumped. Second generation. So we have 300 steps in the generation. Generation 1 was like 50% survival. Generation 2, 75. 78. And this is with very high genome length and 8 internal neurons. Yeah, so I'm not sure. I have to check the code. There's a few things that don't make sense, and I'm not sure how mutation. Oh, actually, interestingly enough, yeah, our parameters, when you change the genome length and internal neurons, everything resets, but you can't change the mutation. But then it doesn't make sense. Yeah, if there's any experts in genomics, do let me know. Mutation of 10%. Yeah, I think we're having a few issues in the code, but I wouldn't even know how to go about fixing it. Well, I guess that's what we have Gemini for. So everything we do is eventually available on BioniChaos.com. Go check it out, provide your feedback, because everything is under development as well. So your feedback will actually make it into the prompts for future web tool applications. And that's the original video by David Randall Miller. The video had a whopping 4.3 million views from 4 years ago. And very interestingly, that was essentially the only, well, there's only 2 videos on the channel. So the channel didn't evolve very well. I don't know. Maybe the video was like taken from another source or something, not sure. Anyhow, this simulation is dynamic. In the video you just see yeah, you can't play with it, it's not interactive. Yeah, you have a lot of videos for simulations like this Fourier transform visualization, And again, in our case, it's dynamic. You can actually go play around with it. You can also do whatever the screen says. You can see, ooh, what's up with that? You can set your number of vectors. Yeah, when changing the vector size, it's doing this funny thing, but once you set it, it's then working better. So yeah, like, subscribe, unsubscribe. You know what to do. You know what to do. And we had another, so we'll get back to more biomedical stuff, biomedical imaging stuff. And we will do, oops, wrong window. Yeah, again, this will be available in production as well. Yeah, it's another data set. I will do an overview on that. By Notebook LM. So this video was brought to you by, well, it's not really sponsored, but you know what I mean.
Imagine for a moment peering not just into the most delicate parts of the human body, but actually gaining an understanding, a really deep understanding that could, well, literally transform how we diagnose some pretty life-altering conditions. We're talking specifically about the human eye today, and we're opening a remarkable window onto this because we're about to take a deep dive into the HRF Image Database Viewer.
Right.
Now, this isn't just, another piece of software. It's described as a powerful, specialized platform developed by BioniChaos, and it gives this incredibly detailed view into high-resolution retinal images.
Mm-hmm.
So our source material today is basically a detailed description of this interactive tool and the database behind it. And our mission really is to unpack this sophisticated platform, not just for the medical folks or researchers, but for you listening in.
Yeah, make it accessible.
Exactly. Think of it like a shortcut, maybe, to understanding a critical kind of quiet revolution happening in medical diagnostics. It shows how this cutting-edge tech is streamlining things, accelerating the path to insight. We're here to pull out the really impactful nuggets, no fluff.
And what's really fascinating, I think, is how such a precise, almost technical tool can act as this foundational accelerator, for medical breakthroughs. It's just a prime example of really targeted innovation.
Absolutely. So, okay, let's start exploring. Let's really get a handle on what we're looking at when we talk about these fundus images. Essentially, these are high-res photos of the retina, right? Back of the eye.
That's right.
Now, for me, it's not just about seeing the eye structure. It feels like a vital, sometimes surprising window, not just into eye health, but often into a patient's, broader health picture, too. Why is this view so critical?
That's a really crucial point. These images are absolutely foundational. And the why they're so indispensable, it really boils down to their ability to help with early detection and managing severe eye diseases. We're talking things like diabetic retinopathy.
Which is a huge issue.
A massive issue. If you don't catch it early, it's a leading cause of preventable blindness.
Yeah.
And with diabetes rates rising globally, it's incredibly concerning. And then there's glaucoma, often called the silent thief of sight.
Right, because you don't know you have it until...
Exactly. It progresses so sneakily, often no symptoms until there's significant irreversible damage. Fundus images let clinicians spot these problems at the very beginning, potentially saving someone's vision, their quality of life. And the blood vessels you can see in these images, they can even offer clues about other things, systemic conditions like hypertension, maybe even some neurological issues. It makes the eye a surprisingly holistic diagnostic window.
That really does underline their importance. Okay, so tell us about the actual database then. The one at the heart of this viewer, the HRF high-resolution fundus, I assume? What makes this specific collection so valuable for researchers, for clinicians?
Precisely. High-resolution fundus.
Yeah.
The HRF database, it's meticulously put together, and its real value is in its precision. It's got 45 high-resolution images, carefully categorized,
Yeah.
15 from healthy individuals, 15 from patients with diabetic retinopathy, and another 15 from people with glaucoma.
Okay, a balanced set.
A balanced set, but what really elevates it, what makes it the gold standard for analysis, and this is key, especially if you're interested in how AI learns up, right, is that every single image comes with manually labeled vessel segmentation maps and field of view masks, or FOV masks.
Manually labeled, so actual humans drew on these.
Exactly. Think about it. A team of experts painstakingly outlined every single blood vessel, and they precisely defined the usable area of each image. This isn't just, lots of high-res data. It's perfectly annotated ground truth, unassailable. For AI development, where the machine learning models are trained by looking at examples, having data labeled this perfectly, it's absolutely critical. It cuts down on initial bias, provides flawless training material, basically. It ensures the AI learns from the best possible human-validated information, so the models trained on it are incredibly robust, reliable.
That's a critical distinction, isn't it? It's not just big data, it's perfect data, meticulously prepped to teach the algorithms. Okay, so with these gold standard images as the foundation, let's talk about the viewer itself. The HRF Image Database Viewer. It's described as an interactive, high-performance platform designed to make these super intricate images accessible. I'm picturing it like a specialized, high-powered digital microscope for doctors and researchers, built for efficiency.
That's a really good analogy, actually. It is built for detailed analysis, but without unnecessary bells and whistles. One of its core things is the ability to toggle overlays, which means you can switch on or off the FOV mask and the O-vessel overlay whenever you want. The FOV mask, like we said, just highlights the precise, usable part of the image.
Right. Cuts the clutter.
Exactly. It's like shining a spotlight only on the relevant bits. So a researcher isn't getting distracted by the periphery, which might have artifacts or just stuff that doesn't matter. And the vessel overlay, that superimposes those manually drawn blood vessels onto the image, which is incredibly useful for, say, instantly checking if an automated algorithm got the vessels right, or for spotting tiny vascular issues that might be hard to see otherwise.
Makes sense.
And it's not just toggling layers. The viewer also has smart filtering and sorting. Imagine a team studying patterns of microaneurysms in diabetic retinopathy, maybe across different age groups. With a few clicks, they can filter instantly. Healthy, diabetic retinopathy, glaucomatous. That makes comparing things super efficient.
Yeah, speeds things up.
Totally. Then they can sort by index or category for structured reviews. And for really close inspection, there's the full-size image viewer. Lets you zoom right in on every tiny detail. Plus, to keep the workflow smooth, it has keyboard shortcuts, one for FOV, two for vessel-esque to close. Everything's about speed and focus.
I really appreciate that kind of technical detail, that finesse, especially when you're dealing with such, high-stakes data. Our source also mentions something called a lazy loading mechanism for performance. Now, for those of us who deal with huge data sets, that sounds pretty crucial. Can you break down what lazy loading actually means here and how it helps keep the experience smooth, even with these massive high-res images?
Sure. Lazy loading is basically a performance trick, an optimization technique. In simple terms, it means the viewer doesn't try to load every single massive image file into memory right when you open it. Instead, it only loads an image when you actually need it, like when you scroll to its thumbnail or click to see it full size. So if you're just quickly scrolling through the small previews, only those small versions load. Click to view the full image. Then it fetches that specific high-res file.
Got it. So it doesn't bog down the system?
Exactly.
Yeah.
It stops the application from getting sluggish or, even crashing under the weight of all that data. It makes sure you get a consistently smooth experience, which is vital when clinicians or researchers are working fast, looking at really detailed visual info where every second counts. It's a classic example of that no-fluff engineering approach. Just pure focus on efficiency and usability.
Which really brings us neatly to the bigger picture, doesn't it? We've dug into the what and the how of this pretty powerful tool. But now I want to pivot to the so what? What does all this actually mean for the future, for medicine, for research? Because this HRF viewer, as capable as it is right now, it really feels like it's built to push boundaries.
That raises an important question. Right now, the viewer's immediate impact is pretty substantial. It definitely speeds up research. It enhances medical training by giving people this easily accessible, high-quality reference point. Its main usefulness, though, is its direct role in developing and validating algorithms, automated analysis algorithms for these retinal images.
Ah, the AI connection.
Exactly. This is where AI starts to directly intersect with traditional diagnosis, because this viewer provides the foundational, perfectly labeled data sets that machine learning models absolutely need. They need it to learn how to spot anomalies. It's essentially building the intelligence that's going to power future diagnostic tools.
Okay, right. And here's where, for me, it gets really interesting because the source material, it also talks about future directions, the roadmap for this platform, and it involves some pretty significant advancements. This is where we see the truly audacious vision for where this tech is headed.
Precisely. Yeah, the roadmap lays out several, well, exciting enhancements, as they put it, pushing the boundaries of what the viewer can do. One key thing is integration of more data sets.
Okay, more data.
Yeah, they plan to bring in other public fundus image data sets, things like Drive and Stare, which are well known in the field. Connect that to the bigger picture. It creates a much more comprehensive research hub. It means AI models can train on a wider variety of images, different people, different cameras, different ways diseases show up. That makes the AI more robust, more generalizable, less likely to get tripped up by new data it hasn't seen, ultimately more reliable in a real clinic.
Makes sense. Broader training, better performance.
Exactly. But the really groundbreaking part, and maybe depending on your view, the most thought-provoking, perhaps even darkly funny part, is the planned AI-powered analysis.
Okay, here we go.
Future versions are going to have integrated AI models. They'll be able to do real-time automated vessel segmentation, meaning the computer just instantly draws the blood vessels for you, frees up valuable human time. Even more critically, they're planning lesion detection, spotting subtle things like microaneurysms or hemorrhages, tiny indicators, often microscopic, but crucial for early diagnosis of, say, diabetic retinopathy. And here's where it gets, well, particularly fascinating, or maybe a bit ironic. The AI will also offer diagnostic suggestions.
Diagnostic suggestions from an AI. That sounds efficient, almost like the AI is just quietly saying, "Psst, hey, doc, maybe check this out. You might have missed this, just a suggestion." It's incredibly direct, a real no-nonsense approach to diagnosis. How do you see that actually working in a clinic? How does it affect the workflow?
It's the ultimate no-fluff diagnosis, isn't it?
Yeah.
Just the AI's best guess based on the data. The way it would likely work is as an immediate kind of silent second opinion. Clinician looks at an image, and the AI, humming away in the background, flags potential areas of concern or maybe offers a preliminary classification. It's not really about replacing the human expert. Not yet, anyway.
You're like an assistant.
Yeah, more like providing an instantaneous, incredibly efficient filter. It lets the human clinician focus their brain power on validating what the AI found, thinking about the patient's whole story, their full clinical picture, and then making the final nuanced diagnosis. It shifts the job description a bit. Less raw data crunching, more sophisticated validation, and patient-focused decisions.
Interesting shift.
And beyond that, they're looking at advanced visualization, things like 3D reconstruction of the retina from stereo images, and dynamic visualizations to compare how different AI algorithms are performing against each other. Imagine visually seeing the strengths and weaknesses of different AI approaches right there on the screen.
That would be powerful for development.
Definitely. And finally, bringing the human element back in, they're developing collaborative annotation tools.
Okay.
These would be secure, web-based tools allowing researchers anywhere to share findings, work together on annotations, and basically speed up discovery collectively. It's about building this connected global research community, all powered by this really precise data.
Which brings us right back to that provocative thought we touched on. Given that tools like this HRF viewer are clearly paving the way for AI to offer these diagnostic suggestions, to sort of silently prompt the human clinician, what then becomes the most critical, the most irreplaceable skill that only a human doctor brings to the table in the future?
It's a huge question, isn't it? It really forces us to think about redefining human expertise in a world that's becoming increasingly augmented by AI.
So we've taken quite the deep dive today into the HRF image database viewer, a genuinely powerful and clearly evolving tool from BioniChaos. We've seen how it makes incredibly complex medical data accessible, analyzable, from its basic job of viewing high-res images with those critical gold standard segmentation maps and FOV masks, all the way to its pretty ambitious plans for advanced AI integration. And this isn't just about looking at cool pictures, it's about speeding up research, enhancing medical training. It's a tool in the fight against serious eye diseases like diabetic retinopathy and glaucoma.
Absolutely. Practical impact.
And as we've explored, the future points towards AI offering those diagnostic suggestions, quietly helping refine the whole diagnostic process. That's a fundamental shift. So here's something for you to maybe chew on as you go about your day. Given that these tools, like the HRF viewer, are setting the stage for AI to offer these kinds of diagnostic suggestions, allowing machines to efficiently flag anomalies, what then becomes the most invaluable, the most irreplaceable skill that only a human clinician can bring to the future of medicine. This rapid march of technology in healthcare is truly something to watch, and yeah, consider its profound implications.
Will be a lot more work on this one done. Currently, yeah, everything seemed to work in general in terms of reviewing the dataset. There's a few funny things with the lazy loading of the images, then causing the shortcuts to behave in a funny way. But that should be an easy fix for, well, any AI tool, a language model to sort out. Yeah, I would like also, when we have it full screen, to be able to toggle the overlays, the vessel overlay and the FOV mask. And and hopefully later we'll be training on this as well, so stay tuned. And one last thing. Yeah, we'll do an overview of this one, and this is directly about AI, different types of AI. Generative and deterministic algorithms, and who is better than Notebook LM to do an overview on this one. So this one should be short, only 6 minutes. So there you go. Let me know if there's any questions. Go check the website. If you have anything specific, do let me know. Issues, problems, complaints, relevant to the website, of course.
Welcome to the deep dive. Today we're looking into AI's surprising split personality. We're really digging into this core tension in artificial intelligence. You've got one type that's all predictable precision, and then there's this other kind. Wild, creative, totally unpredictable. Think of them as this like digital odd couple, always clashing, but now increasingly they're being forced to work together.
Yeah, and what's really fascinating, I think, is how these two types, deterministic and generative AI, they really show this fundamental duality. One gives you that absolute certainty of logic, rules, like a super meticulous accountant. And the other one, it just thrives on probabilities, on learning patterns, and, well, basically invention. It's more like your bohemian Argus type. So our mission today is really to unpack that difference and figure out why it actually matters for you, especially as you're trying to navigate all this.
Okay, so let's start with the meticulous accountant. Deterministic AI. What does that predictability really mean in practice?
It means, quite simply, same input, you get the exact same output every single time. And it's predictable because it's running on these very specific, explicit rules and logic that humans have coded into it. The decision making. It's transparent, you can see inside, it's a white box. And that auditability, that clarity, well, that makes it essential for critical stuff. Think financial fraud detection, maybe some medical diagnostics.
Right, where you need to know how it got the answer, not just the answer itself.
Exactly. It's not just about reliability, it's accountability. Could be legal compliance, could even be life and death.
Okay, so the ultimate rule follower. Got it. But let's flip to the other side. The wild artist, generative AI. This feels completely different. How does it even work?
Well, unlike its deterministic buddy, generative AI is all about probability. It looks at massive, massive data sets, learns the patterns, and then, using these really complex statistical models like billions of parameters, it predicts the next most likely thing in a sequence, a word, a pixel, a note of music. And that lets it just conjure up totally new, seemingly original content, text, images, code, you name it.
Wow.
What's really interesting is that for the same prompt, the same request, it can give you different outputs, which is great for innovation, right?
Yeah.
Amazing creativity. But, and this is the big but, its reasoning comes from those billions of connections, those weights. It makes it fundamentally opaque, a black box. It's incredibly hard, sometimes actually impossible, to know exactly how it got from A to B.
Okay. So it's like the brilliant collaborator who just shrugs when you ask them how they came up with that idea.
Yeah.
Bit unnerving. So where do these two personalities, this digital odd couple, where do they actually fit in the professional world?
Well, a key thing to see is that industries with, high risk, lots of regulation, they naturally lean towards the predictable, deterministic systems for their core stuff. Think where you need objective correctness against a known truth, like air traffic control, maybe.
Or my car brakes working exactly the same way every time I hit them, please.
Precisely, yeah, exactly.
Yep.
Or ensuring your anti-lock brakes work perfectly. Reliability there is just non-negotiable.
Right. Okay, meanwhile, you've got the creative fields, marketing, writing, game design. They're jumping all over the generative tools for that innovation boost. Where it's more about subjective quality, does it feel right? Is it interesting? It's almost kind of ironic, isn't it? The most creative AI is the one we understand the least. Sometimes it gives you gold, sometimes it's just plain weird.
And that really gets to the heart of it. A model's biggest strength is often tied directly to its biggest weakness, the deterministic system. Super reliable, but also kind of rigid. It can't easily go beyond its programming, the generative one. You get that amazing creative freedom, which is thrilling, but it comes with risks, unpredictability, inherent biases from the data, and these lovely things called hallucinations.
Yes, where it confidently makes stuff up.
Confidently presents complete falsehoods as facts. Yeah, it's a trade-off.
Yeah.
You're dealing with fundamentally different beasts.
But okay, the future isn't just picking one side, right?
Yep.
Certainty versus chaos. What happens when this digital odd couple doesn't just awkwardly share an apartment, but actually starts collaborating? Maybe even a shotgun wedding?
Huh. Well, that raises the key question, doesn't it? What does happen when you combine the best parts of both? And the biggest trend we're seeing right now is exactly that, the rise of hybrid models.
Okay, like ARG. I keep hearing about ARG. Retrieval augmented generation.
Exactly. RX is a prime example. So imagine you ask your AI a really factual question, something like, what was our exact Q1 revenue last year?
Right. You want the real number, not some creative riff on finances.
Precisely. So with RAGI, the brilliant thing is the deterministic part acts first, like the super diligent librarian. It goes into a specific controlled database, your company's records say, and retrieves the precise factual data point, the actual Q1 revenue figure. Then, only then, does the generative part kick in. The creative LLM gets your original question plus that verified fact retrieved by the deterministic system.
Okay.
So it can then craft a natural fluent answer like $5.2 billion using its language skills, but it's grounded in the verified fact. It's basically like giving your slightly unpredictable creative genius a dedicated fact checker and a very specific library to work from.
Okay, that makes a lot of sense. So wrapping this up, what does all this mean for you listening in, trying to navigate this world where certainty and enigma are sort of colliding?
Well, maybe the really provocative thought here isn't about which AI is, better, but more about how we as the users have to grapple with these trade-offs. It's fundamental. We're increasingly relying on systems we can totally understand, these white boxes, for the really critical stuff. And at the exact same time, we're leaning more and more into these other systems, the black boxes that we explicitly cannot fully interpret precisely because they can generate novelty. It's a trust exercise, really, with real consequences.
So what will you choose to trust with your next big question? The predictable certainty, the one that might sometimes limit possibilities, or the creative opaque enigma, the one that might sometimes generate brilliant lies? Keep diving deeper.
We're making powerful biomedical tools accessible to everyone.
Ever wondered what your brainwaves sound like? Or look like? Ever wanted to play with real scientific tools? Ours are free and open source. You won't believe what you can do with your own data.
Want to dive into data science? Start with our interactive tools. Go ahead. Play with the data.